Alright, well, good morning, folks. My name is Cameron Nixon, and welcome to Mesoscale Musings. Today is April 12th, 2020, and we've got a pretty substantial forecast on tap. The Storm Prediction Center outlining much of Mississippi and Alabama into Georgia and flirting with Louisiana in a moderate level 4 of 5 risk for significant severe weather. With a broad area of enhanced risk around that as well. So extremely difficult day on tap to forecast because there are a lot of moving parts. And I know there are some newcomers and up-and-comers, I guess I should say, to the meteorology world potentially watching this as well. So I'm going to do something a little bit different today and really break things down from the bottom up, and we're just going to piece apart every single piece of this event and see what is making it what it is. So as always, I want to make sure that these forecasts are for educational use only. These are not forecasts based on the Storm Prediction Center, on probabilities, on individual people, or even chasers. This is a exploration into the dynamics that produce supercells and other rotating things in the atmosphere. So if they coincide with other forecasts of severe weather, great. If not, this is simply my unbiased analysis of the atmosphere and where isn't conducive for supercells and tornadoes. So let us begin. This is a pretty sexy, if I do say so myself, sounding from Slidell, Louisiana. That's toward the southeastern portion of the state. And what we got here is a very eye-popping elevated mix layer. That's where our temperatures decrease rapidly with height. You can see here the maximum is about 7.8 Celsius per kilometer, which is very steep for this kind of area, leading to some pretty pronounced thick cape, especially in the 6 to 9 kilometer region. Most unstable cape reaching over 2,000. So really loaded thermoprofile. You can see there's a very strong cap where you do have a temperature inversion with height. And that is going to be pretty difficult to break with this sounding, but we'll talk about how this could be altered to make this easier to break. And, I have no problems at all with this hodograph. There is very strong shear, very strong curvature, but we'll go into a little bit more detail onto these components as well. First I just want to do this little exercise because, again, I know there are people of every walk of life that could potentially be interested in an event like this. And you know what? Let's just pull up significant tornado parameter. All right, let's just do the dirty deed. We got SIGTORs over 10. We got it maxed out over much of this area. So what does this mean? Think to yourself, what does this mean? The significant tornado parameter is meant to delineate the environments of significant tornadoes, which are EF2 and greater, and those below. So using this map, where are the most powerful tornadoes going to be? Where do we have the ceiling for EF3, even EF4 tornadoes? Where is our greatest potential for longer tracked tornadoes on here? Where's our greatest probability that we're going to see a tornado? Keep in mind all these things. This map will not tell you that, and so that's why we go into very in-depth discussions over a broad range of operational meteorology offices. This is not going to tell you a lot of things. And so we need to kind of break down what makes a significant or long-lived, discrete tornado environment from something that isn't. So that is going to be the purpose of this discussion, because this is a very high ceiling and also low floor scenario today. There are many ways that we do not get long track, powerful tornadoes, and there are a couple ways that we do. So I'm going to explore both of those in this discussion. So starting from up top, let's zoom out a little bit. Got our 250 millibar jet. This is actually a pretty classic configuration for the southeast, perhaps quite a little bit south, I guess I should say. Often these scenarios line up with this really powerhouse jet coming across kind of the southwest U.S. But this is really digging into Mexico, and we can talk about more impacts of that later. So, sorry, I thought I was not recording this and I started freaking out. And once this noses into the area, you can see there's some pretty strong diffluence in this jet. We have our jet exit region here, and then you have this piece of energy that's really lifting quickly. I mean, think about this. Over the course of only a few hours, you have this really strong wind max in the upper levels forming and cruising up into the Great Lakes. It is really cool to see some really strong synoptic dynamics at play there. And so this strong divergence and the coupling of these jets, you want where your greatest lift is going to be between kind of your left exit region usually and your right entrance of this northern jet. And that is where you can get some really strong low pressure centers to form, especially in this scenario. So this is going to play a role today. And as soon as this jet noses its way into the region that we're discussing, really strong shear values could ensue. We got over 130 knots on this jet streak. So that is also going to contribute directly to supercell dynamics. So we go a little bit lower, look at a 500 millibar vorticity, the spin in the mid-levels of the atmosphere, and we could track these vorticity centers and kind of estimate where they're going to kind of end up by looking for the advection of the stronger vorticity values across, we're looking for flow through the isobars across these centers to kind of move them along. So we got flow kind of through this little knot in our height falls here in this trough. And so this is probably going to push this vort max a little bit, potentially even southeast for a few hours. If I drag this out, it's kind of sort of what happens. Maybe it moves a little bit east. But as we keep going, we see that it starts orienting a little bit more vertical. And then you get a little bit more vorticity advection kind of out ahead of this little pocket, which is going to start to drive this thing up north and drive it up north quickly. So if I scoot this out, that's pretty much what happens. It starts cruising through kind of the northernmost portions of the outlook area. And what these mid-level vortmaxes do, in essence, are provide the mid-level forcing for either large convective complexes or low-pressure centers. So usually the action kind of follows where these things move. So if I skirt this out, you could see that a lot of the moderate risk area is actually centered to the south of where this vortmax is progged to move. So we'll discuss why that is. But I also want you to pay really close attention to just how strong of dynamics we have right ahead of this thing, especially as it moves into northern Mississippi and into Tennessee. Strong dynamical systems like this, combined with the instability and moisture we have today, rarely don't lead to really dangerous scenarios, regardless of convective mode. So we'll talk about what kind of convective mode is possible up here, and why it could still be a pretty dangerous event. I was going to do 700 millibar vorticity, but you could actually find it on this water vapor map right now. Let's actually turn on radar first to make this really apparent. We have this complex of storms over northeast Texas right now, kind of originated near the Del Rio area overnight. And this thing is visibly rotating. We got a little bit of lagginess, but yeah, this storm complex is visibly rotating, and this is kind of the manifestation of our mid-level vortmax. And you could also see it in the kind of cloud features that it produces. There's rising motion on the eastern side of the wave and sinking motion on the western side of the wave. And I guess if you don't believe me, I can pull up 700 millibars as well and kind of skirt up to about this time. And you can see there is this kind of lobe of height falls here and a vort max about here. And this is what is going to kind of phase into this big kind of trophy mid-level vortmax system that we've been discussing. So really cool, and you could physically see all the sinking motion behind this with the dryness this is low-level water vapor. So I don't know my product completely well, but this is probably around the 850 millibar level from what I remember. So you get this dry air streaming behind this. This is also going to pose a complicating factor for the cap today that we were just discussing right here, which is centered around 850 to a little bit above that. So this air is coming from the high plain or the high terrain in the Mexican plateau. They've had a pretty prolonged last couple days downsloping wind event from this kind of flow pattern that we've been in. So you get this really strong flow over the Mexican plateau, and what results is at the bottom you get strong adiabatic warming, and I can push this out and you can see the remnants of that kind of on the eastern coast here. We got temps modeled by the RAP to be over 100 at times. So that's hot air, and adding that to this cap is not going to bode well if you want a widespread severe convective event, because we're going to have to find ways to break that cap. Even with other ways we could break this cap are mid-level temperatures, and we don't get our really cold mid-level temperatures until you kind of get into this cold core kind of lobe into Oklahoma, northeast Texas, a little bit into Arkansas as well. So this is kind of our more cold core regime, and this should offer us a little bit more cape as well as our mid-level lapse rates steepen, and I can kind of give you a cape map to cheat with, and that's generally where we have most of our cape. So the RAP and NAM model this warm air. You could see it literally coming off the Mexican coast here and toward the U.S. There's very strong advection of these temperatures in the 850 layer toward the southeast. So you can almost bet that this cap is going to get stronger in that sounding before it gets better. And especially because we have so much widespread convective debris. What am I doing here? I can take off radar here. We don't have many glimpses of sunshine, at least yet, in the southeast. So this is the sounding right here looks to hold, right? We have saturated low levels, which is what we're seeing in these clouds, and we got that high kind of finger of high temperatures originating from the Mexican plateau, which is going to keep this here. Our low level or our mid level lapse rates may steepen slightly throughout the day, but I'm not expecting too much of a change from the sounding, at least for most of the day. So let's talk about, so we've got our instability check, we got our moisture check, we got a pretty loaded system with respect to that. So what about our shear? We have in the upper levels, or let's talk about our mid-level 500 millibar jet. We got some pretty, I don't want to say high, but more standard, maybe a little bit high values for this region at this time of year. We routinely get some pretty strong jets here. And ahead of that, this is going to induce a pretty powerhouse low-level jet. And quite northerly, perhaps a little bit anomalous for this region. And what that's going to do is create a very large, rounded hodograph. So we can dissect this even a little bit more. Let's kind of zoom into the southeast. There we go. And let's hit about the 22, 23 Z hour. And what we see here, it's very subtle, but I'm going to have you look really closely. Over the western portion of this risk area, we have a little bit more of a southerly component to this jet, and it's a little bit stronger. And at the easterly kind of portion of this jet, we have a little bit more of a veered, kind of more east-southeasterly, and it's a little bit weaker. And maybe 250 might even prove this point a little bit better. Yeah, so we have these really strong upper levels kind of feeding into Arkansas, and it starts to slacken by the time you get to this eastern portion. So keeping that in mind, we also, once we go down to 850 millibars, this jet axis is displaced quite a bit from the cold core kind of Arkansas region. This is pretty common in cold core events. You have, or at least where you have this really negatively tilted trough. We're way out ahead of your system is where you get your mass response. All these winds to increase in the low levels. And so we have some powerful low jet here, leaving this area with a lot less. So I just ran my infamous kind of hodograph maps. So I figured we would discuss this a little bit. Is this going to work if yeah, there we go. So I can zoom out to the time that we were discussing and the impacts of what we just saw. We have a weaker low level jet that's going to make for a less pronounced hump in the low levels in this hodograph. Out west into Louisiana and Arkansas, and you have an increased low-level jet out east in the axis of where we saw that highest low-level jet. Sorry, we have an increase in this, the dramaticness, I guess you could call it, of this hump in the hodograph. And likewise, we were also talking about we had a really strong upper level flow. Look at that. Our green segments, that's 3 to 6 kilometers. These are really strong, and they're also backed. So we have a lot of, we have a little bit of veer back in our profiles here, and really elongated kind of straight hodographs. Whereas we had our veered and a little bit weaker flow out east. That's actually going to be good for these hodographs because they kind of keep this well-rounded shape to these. So, you know, I'd be lying if I didn't say that 90% of these hodographs on this map, with the exception of kind of moving its way into Arkansas and Louisiana, pretty much all of these have been associated with very long-lived significant tornado events, potentially intense or even powerful. So that is the shear space we're dealing with. But as just as I threw up this map, you could see the impacts of having all of our cape centered on these hodographs that really don't look too fine. And we also have kind of that lack of cape and a little bit more capping over the areas where we have our really good hodographs. And for reference, this is a normalized cape in the 3 to 6 kilometer layer. I just prefer this because it gives me a better estimate of the mid-level stretching in a supercell. So that's why I use this, and values of about, 0.5 to 2 are, I guess, pretty run-of-the-mill of this region. And you start slipping pretty below that. Once you get to around 0.1, this is your really skinny cape, and you really have to rely on the kinematics of your hodograph to overcome that, which you do have some pretty big hodographs. So that may overcome it. But out here, you have some hodographs, and you actually have a lot of thick mid-level cape, approaching 0.3, 0.35. This is when I really start thinking big hail or other large or strong stretching kind of hazards. So with that in mind, why are we depleting the cape in most of our warm sector? Well, that's going to be a problem that's addressed when we talk about forcing, actually. So we need to talk about which areas are going to see the highest probability of convective growth, because our fourth ingredient, our moisture instability shear, in order to get a thunderstorm, you need lift. And lift does more than just give you a thunderstorm, but it allows the organization of individual thunderstorms into complexes. So we want to know what kind of thunderstorm complexes are possible where, and where we have forcing that can more favor discrete supercells instead of these large complexes. So as we talked about earlier, I could zoom in a little bit more on this feature. This is one of the said complexes, and right now it's kind of being given that boost by that mid-level vortmax. And as it's moving into destabilizing air mass, as you could see by all these cumulus clouds, especially potentially in the just off the deck, we might not be completely unstable in the low levels, but we have this strong instability just off the deck. I don't think this thing is going to stop. And this is likely, if you've been looking at convective allowing models, a system that kind of just moves through the entire risk area along that jet vortmax that we were talking about earlier. So strong forcing, strong instability, especially kind of like modeled on the sounding. This thing's going to go on for a while, and this is going to be a very dangerous complex. Because it is likely going to be, you could even see a rear inflow jet in here indicative of some pretty strong winds in this middle portion. This is likely going to deal some damaging winds if our thermodynamic profile is good enough and allows for the mixing of these winds down to the surface, and it could pose an occasional tornado risk, which may even escalate as we add more cape to this. But the one thing this complex and this associated vortmax are going to do is provide lift in its general vicinity, and especially just out ahead of it. We got our sinking motion behind it. We have a rising motion ahead of it. You can see our clear skies behind it, our dirty skies with even some rows of developing showers and convective activity ahead of it. So as this thing moves, these regions are a little bit funky here. I guess this one will do. As this thing moves into the northern portions of especially Mississippi and even higher into Tennessee, if it does make it that high, there is going to be an attendant risk that one of two things happen. One, or a couple cells are able to form out ahead of this, kind of in this fashion, where the broad scale lift from this is enough to trigger kind of either a feeder shower band to kind of ignite, or you can get a cell kind of forming on the flank of this away from the strongest cold pool that's able to take advantage of those wicked shear profiles I was showing earlier, and kind of immediately become supercellular. Or you could even have what is fallaciously known as downscale growth, where you have these shear profiles are just so strong that they do unanimously favor supercell growth. So that's why over the majority of this thing's lifetime, you will see things spinning. I guarantee you, all along this gust front, because the hodographs simply support supercells that strongly. So any one of these convective elements within this could end up breaking apart and becoming supercells themselves. If they do, that is going to be the number one most dangerous scenario for today's event. I will kind of give you a more closer look to that. Again, we showed our hodographs earlier that were, I could just pull this up again, around the 23Z hour, that were very incredibly large. So what these do and why you can kind of guesstimate the potential for significant and longer-lived tornadoes from these is the extremely high amount of streamwise vorticity we have available in the lowest 0 to 1 kilometer. These are top-notch for the southeast, and the next things I'm about to tell you are a little bit lesser studied. These are just some things I've observed. The critical angle, which is the angle between the low-level shear vector and your storm motion, is the higher the angle you get, potentially the higher potential you have of your mesocyclone spinning up a circulation that is able to go tornadic. I've seen hodographs like these out west be really finicky with respect to tornado potential, and it takes these mesocyclones a long time to kind of fully wrap up and produce a low-level circulation. Given the boost that we get from the extra vorticity from along the gust front, of the QLCS. I'm assuming these won't be too much of a problem in gaining tornadic circulations, but it's these rogue supercells we're worried about. That if you're looking for a easy tornado potential, usually you want this critical angle as high as possible, because that indirectly organizes a storm in such a fashion that it more readily produces tornadoes than with hodographs like this. Secondly, this is an even lesser studied concept, is the concept of what is a long track tornado. The definition wise is it is a tornado that tracks for a very long distance and impacting many people. But these can be broken down into two components. We have our storm speed, which is very fast, which is going to make any even brief tornado relatively long tracked compared to what it would usually be. And B, what helps us maintain these mesocyclones for very long periods of time. That is called steady stateness of a supercell. In order to get the most longest track tornadoes, you need your supercell to be capable of producing tornadoes in a steady state fashion that don't occlude or don't kind of fail in one way or another. And one thing I've noticed, a very cheap trick compared to the rest of this theory, and this was even outlined in a Palm Sunday paper I actually read just yesterday, is that a decent way of estimating this is the strength or length of our 0 to 3 kilometer shear vector. So once you get these 0 to 3 kilometer shear vectors incredibly long, this just eyeballing this is definitely over 40, 45 knots, perhaps 50. This is where your chance for steadier state mesocyclones occur. So any supercell forming in this environment, not only is it going to rapidly organize because of our strong veering profile and our higher critical angle, it could keep a low-level mesocyclone on the ground for a very long time. And again, we discussed the impact of our cape on this type of scenario. I do think that if a supercell was able to form with this kind of hodograph, it would last pretty well into this reservoir of lower cape. And again, we'll discuss later why that reservoir could be there. So I guess as a bottom line, this feature took me a while to circle back to this, but I'm here. This mid-level warp max feature is going to be moving through this region of especially eastern Mississippi into western Alabama, perhaps especially the northern portions of this, at about the right time to make the most use of the environment we have today. So that includes the potential for a extremely long track, perhaps powerful tornado, given the juxtaposition of all these ingredients here. And that would especially, again, be favored kind of in this region. So now that we're done with that, that convection will likely die after it makes its way about halfway through Mississippi due to that lack of cape, and then we'll need other options. So another option that we have, so I need to drink a little bit of water. I'm just, this is a discussion. So the other piece of this outlook area we have, I could zoom back a little bit out, is this mid-level convergent zone in our 850 millibar winds just off the deck. This is not really a perceivable surface feature, but we do have it in the 850 millibar level and above. And what that convergence is going to do, you have this really high expansive high pressure out in the Atlantic, and you have this cold air coming down in association with this crashing cold front in Texas, and they both kind of combine and converge to create this narrow channel of moistening mid-levels, and you can see that as we go on. So all that moisture and just off the deck is going to be very good and all that convergence for initiating storms. But the only question is, could this create storms that are elevated, especially at first, instead of surface-based storms. So my theory here is that I hate doing the forecast process backwards. That's essentially what this is. The convective allowing model signal basically does not feature cells in this regime, in this mid-level convergence zone, to become surface-based storms quickly. And I'm guesstimating that it is potentially because all the convergence here is centered at the just off the deck level, not at the surface. So you just get a bunch of forced convection in the mid levels or in the low levels, and this convection starts to proliferate and become more intense, and really saps out the low levels in terms of instability and potential for surface-based storms. So again, that's just my theory on why the convective allowing models are doing what they're doing. But I at this time, at this time, I guess I can't really have confidence in this feature, which would be out ahead of the main low pressure system. So ideally would be good for supercell formation. I don't have confidence in this initiating, especially during the day. So we can go backwards now to the third feature that I think could serve as some lift. Let's zoom back into our area of interest, and that is the Pacific Front. All that is a quasi dry line that has made its way all the way to the southeast. And let's actually look at current observed dew points. And just looking at dew points, there are low 70s ahead of this kind of feature, and low 60s behind it. So this is a very washed out, if you really can't call it a dry line at this point, Pacific Front. And mid-high 70s in front of it, low mid 60s behind it. Very washed out feature. And as I use the wrap data, you can also see that this washed outness kind of continues throughout the day. And this is another, usually when you have these big Dixie Alley tornado events, you're looking for a sharp dry line Pacific Front to initiate storms off of, because we talked about this. We have a really loaded atmosphere here with amazing hodographs, and we just need something to lift a storm or two up to pop it through this region. As we talked about, this complex is a really good way to do that. We obviously run into the issues of, it might not pop out ahead of it, or everything might go linear and stay linear forever. But if we had a source of forcing that was a little bit more diffuse and not cold pool forced, but still convergent and strong enough to produce convection, we would have an outbreak of really dangerous storms. And you could see that through a low level wind field. There's very little in the way of convergence along this Pacific Front feature. So on another day, if we had due southeasterlies coming out of here and these easterlies, this would be a really, really, really dangerous event in terms of tornadoes. But it's not, and we don't really have much to force any storms along this feature. So that's why I'm thinking that the majority of the kind of area that the moderate risk was in won't see storms. It's a very low probability, high impact scenario. This is not exactly favorable for initiating storms. As we go later on in the evening, though, especially combined with the crashing cold front up here, I think we're going to get a little bit more forcing kind of along this front to pop more storms. And once it runs into that kind of simmering mid-level or low-level convergence zone that we were talking about earlier, I'm guessing things could start getting interesting again, especially in the overnight hours. So we can discuss that a little bit. Now. So we still have that sin out here, a residual from the capping inversion earlier on in the day. And we do have our kind of lack of cape here that we've been discussing, likely due to that mid-level convergence zone. But as this line gets closer, especially in the evening hours, you still have a little bit of remnant cape, and you have kind of another channel of this cape that is originating from kind of a higher theta E, higher dew point regime just west of Florida. I've noticed this kind of just off the coast, this northwest coast of Florida, is a little bit cooler in terms of our dew points and our temps. So that might be another thing inhibiting some of our cape up here. But as you draw this out, this kind of second plume starts to advect up here. And this kind of area seems a little bit more ripe for severe convection. And that is especially kind of in the overnight to early morning hours. So, what should we do now? Let's go and kind of dissect time frame by time frame what all three of these forcing mechanisms could look like throughout the day. So first we have this strongly forced system, and as we discussed, I don't think there's a reason for this to stop cruising all the way into northern Mississippi, even into Tennessee, perhaps even higher. So this is likely going to be, this very well could be the most densely populated in terms of warnings and reports. And most of those will fall under severe and severe wind gusts. And then you could potentially have a smattering of tornado reports within that as well, because this is a strongly rotating QLCS. So if I'm not going to use Pivotal Weather today because they've been a little sore from all its users clicking on its sounding, so it takes a while to load. But I can kind of go in this general northern Mississippi region about the time where this thing waltzes in there. And again, putting everything together, this looks about right. This is kind of between our two hodograph regimes. If you remember from the beginning, we had our very long looping hodographs out east, and you had our little bit straighter veer back hodos out west. So this is kind of a good in-between example. One thing I forgot to mention is these very not steep low-level lapse rates in this very saturated layer here. This is a hallmark of strongly forced events. Rich Thompson from the SVC does a great video on YouTube on this if you search Rich Thompson workshop and synoptic ascent. And what these large-scale synoptic systems do over a long period of time is they kind of raise this height at which this moist layer goes up to. So this is not necessarily ideal for low-level circulations, and especially for the mixing down of severe wind gusts, because you want more dry adiabatic lapse rates, because that means you have more convective overturning. We don't have that here, so this system very well that we're talking about here very well might not be able to mix down. It's a very fine line. It might not be able to mix down some of these strongest winds to the ground, so we'll have to keep an eye on that. But as you can see, we do have our highest cape values in the upper levels, so this will assist in our downward momentum transfer as well, because what goes up must come down. So pretty good sounding for the maintenance of a QLCS, especially with all that cape above there, and the potential for a few spinnies in there as well. So I could carry that out. What was really, I'm going to switch to supercell composite just so it's easier for me to delineate the areas. Again, I'm not using this for any other meteorological value except for that. I moved this out into western Tennessee kind of in the early evening hours, right? It's still about 8 p.m. their time, just ahead of the system. And you still have that really deep moist layer, perhaps even getting some sin there. You can see that dashed line behind there is the actual virtual temperature, which is what the sounding is based off of. So you might start getting some convective inhibition overnight. But you still have these really good hodographs with lots of streamwise vorticity, a little bit skinnier cape, but still very sufficient. So any storms coming from this complex will still continue to do their thing well into the evening hours. Let's poke it around midnight just for fun, into the Tennessee-Kentucky border. And same scenario, actually looks like you get a little bit more low-level cape, and that's likely a result of coldening, if that's a word, mid-level temperatures working its way into the region, allowing for steeper low-level lapse rates. And combined with a hodograph with lots of streamwise vorticity, I like to call this one the forever meso hodograph. These are just exceedingly favorable for circulations that last for very long periods of time. So whether or not a tornado is actually on the ground, any QLCS circulation, especially in the overnight and to early morning hours, or I guess I should say evening to overnight hours, especially, will be pretty conducive for some longer-lived QLCS circulations. So the next possibility that we had for severe weather was, again, that rogue supercell that formed out ahead of that complex. I think that could be aided potentially by a warm front surging into this area. So just trusting wrap with this again. This is kind of blind, but this will give you the idea. This warm front moving into the northern border between Mississippi and Alabama by about 23Z. I'm assuming that's when this warm front forcing combined with the forcing from this complex are going to kind of maximize and add to each other. So we could put a sounding about 23Z kind of in this general area to see what's going on. Gonna take another swig. And you can see that's still a remnant deep moisture pool, but our hodographs are a lot more manageable for rapid supercell growth, especially than those straighter hodographs out there. I think as soon as you go a little bit east of there too, start getting into that more wild territory. Yeah, exactly. So again, these low lapse rates are going to be an issue. I think with these shear profiles that a supercell that's already ongoing can kind of drill through this. These are extreme values of shear and SRH, but they could still be an issue. And there's a real potential that a lot of cells in this area are not able to take advantage of that stable layer and produce severe weather at the surface. So our third regime was that, or our second regime was that kind of convergent zone at 850 millibars. And if I draw this out, again, we kind of came to the conclusion that the late evening overnight hours could be the best for severe convection off that, especially once that Pacific front works its way in and collides with it. So I could kind of put something off into eastern Alabama. And it seems like your low lapse rates are a little bit better. I'm wondering what that is a cause of. Ooh, that's an interesting. I wonder, this is now pure speculation, I wonder if some of these lapse rates are better because the state of Florida is a landmass and heats up during the day, and all this low-level flow brings that into this area. That would be really interesting. Let's do 850 millibar temps. Yeah, this is an interesting signal. Yeah, because it looks like this moisture plume is still going to be an issue. But if we cool our mid levels from any convection that occurs with that convergent zone throughout the day, we might be able to add to this cape. I'm not sure what's exactly causing this. I want to believe the main impact of this, or main impact to this, are those warm temperatures over Florida throughout the day, which would be really fascinating. But just like any sounding, this one is still conducive for longer-lived, potentially intense, even powerful tornadoes, given the right convective mode. So the only issue I have with that is our shear vector line orientation, which if you cruise on later on during the evening, this line does become a little bit more parallel, I guess, especially as you work your way into the morning hours. So there is a chance that even if this line isn't incredibly soupy in mixed mode with the occasional supercell, there is a chance that forcing along it with the shear vector that moves these storms closer to along this line, there is a chance that this makes this extremely messy, and this line also really doesn't do much. So again, we've covered two targets that have really good potential to deal discrete supercells with tornado potential, but also a pretty good potential to completely underperform, unfortunately. But again, this is another high ceiling, especially because you have stronger forcing and a longer line here. The ceiling is there for quite a few supercells capable of dealing significant tornadoes throughout this area overnight. So that's a concerning spot. And one last region that I was looking at was, let's do theta E first, was kind of along the eastern portions of this warm front, where we do have another stream of moisture coming from the eastern coast of Florida, working its way up into Georgia. Again, Florida is a little bit of a nuisance for blocking this flow, but this should work its way up into middle Georgia by kind of later day, yielding some higher Cape values and kind of a zone along the warm front that is favorable for supercells. So this warm front is another source of lift, as it always is, because you're getting low flow over it and kind of raising those parcels. And if I poke around Georgia, there is still a favorable hodograph and sounding for significant, perhaps. Yeah, COD does this issue every once in a while. I just gotta click again. So still very long hodographs, lots of mid-level veering, and some pretty robust low-level cape across this boundary. Warm fronts are usually very good for low-level instability because you're quickly pushing in that warm, moist, unstable air near the surface, and that usually ends up with some pretty steep lapse rates near the ground. So still a significant tornadic sounding all the way out into Georgia. This, again, could be a late afternoon kind of event before the main wave arrives later on in the day. So, the last regime, just for fun, I know our lovely hodograph map here delineated lots of cape into Arkansas and northern Louisiana. So what would force that? Well, the cold front, all the way behind our system. Again, this is kind of a wacky system with regards of where our pieces are placed. But as our cold front moves in, we will have some pretty high values of cape take over just out ahead of it. And that cold front may be enough to spark a few thunderstorms that end up producing or turning into supercells. So I can get a generally representative sounding there. And it's going to be hugely different from the rest of the areas we saw earlier. But then your cape is very large. You have some very dry mid-levels and a very straight hodograph. This looks pretty prime, especially with some strong shear above 3 kilometers. Pretty prime for longer-lived hailstorms if you get a storm or two in this environment. Would not be surprised to see kind of like an arc of potentially hailers traversing southern Arkansas and perhaps northern Louisiana and northern Mississippi. Then this would be behind our main, our main shortwave here. This would be behind it as the atmosphere is likely able to recover behind it with those steepening mid-level lapse rates and the return of moisture behind the system. Later on, this might end up congealing into some sort of linear fashion due to it being roughly parallel to the mid-level shear. And with all that forcing, especially closer to our upper level low. And if we plot a sounding around there, it's virtually the same thing. Even in the evening hours, you have some pretty robust low-level CAPE and mid-level lapse rates, and still your straight hodographs. So again, I think this area could be a hotspot later on in the day, into the early evening, after this first system gets through, for the potential for some swaths of hail and potentially even damaging winds, because I can go back to this. The low levels of our sounding are a lot less plagued by that deep moist layer, and you get a little bit better of lapse rates down here as well. So if you're looking for damaging wind potential, it could definitely be kind of a sleeper event into the early evening with this. Well, oh my God, I'm out of breath, and I thank you for joining me on this adventure. Again, these things excite me to no end, and you know, this is a place or a space to be able to be excited about events like this, because for me, I'm a researcher, and I want I love watching these events unfold. Because they just continue adding to my base of patterns and outcomes, and it just fascinates me. And you know, if you're watching this, don't feel like you have to suppress it. Obviously, read the room and be empathetic, because these are incredibly high impact events, and if you end up saying the wrong thing to someone, that's not good. So please avoid doing that. But you know, to the scientists and us, this is incredibly fascinating, and you need to embrace that sometimes. So thank y'all for watching. I'm exhausted after this, but I hope you take away something or some things from this, and really put into perspective what it means to predict tornado potential on supercells. So yeah, have a good one, everyone.